Hello everyone. So today we're going to do an example of arc length and one example of area of a sector of a circle. And there's formulas for both. On my first page here I have an example that's dealing with arc length. So the two formulas that you can use for arc length, one is for degrees and the other is for radians, depending on what your theta is given in. So S equals theta out of 360 times 2 pi r is the formula that you can use if your theta is in degrees, because it's just a fraction. The arc length is a fraction of the total circumference, and 2 pi r is representing circumference. So that's kind of an easy way to remember that formula. But then if your theta is in radians, S just equals r theta. So that's for if your theta is in radians. And arc length is just, if you have a circle, and then you have a certain angle in the center, and then the radius of the circle is r. The arc length is like this on the outer edge of the circle, so that's the S that we're talking about. I can just highlight it. Now this example that I picked is one of the more challenging examples of how to use arc length. So it's stating that at its closest approach, Mars is about 5.6 times 10 to the 7th kilometers from Earth, and its apparent size is about 0.00012 radians. And then they're asking, what is the approximate diameter of Mars? The way that you can draw this picture and visualize this is, here's us. We're just a tiny dot on the surface of Earth. We're looking over in the sky at Mars, which is a pretty tiny planet. The apparent size that they're talking about, our eye can see the shape of Mars, and if we were actually able to measure the distance from the top to the bottom of that tiny Mars in the sky, that's its apparent size, which, since it's measured in radians, that's kind of easy to remember that it's this angle right here, 0.00012. So that's actually the theta that they're telling us. Now, the diameter of Mars would be if we could draw like a curved arc over there on Mars. That would represent the diameter, and it would be roughly the same thing as the S, or the arc length, in this picture. And then the distance that the two planets are apart from each other, that can be measured straight across, and let's just say it's one of these lines that I already drew. So it's 5.6 times 10 to the 7th kilometers right there. So if you imagine this as part of a bigger picture, I'll just kind of draw a small dotted line. Okay, that's not a very pretty looking circle, but if you imagine that, here we are at the center of this big huge circle. The 5.6 times 10 to the 7th can be used as the radius, the r. The arc length is the diameter of Mars, which is what we're trying to find. And the apparent size is the theta. And that's easy to remember because it's measured in radians, which is how we measure an angle. So all we have to really do is plug these numbers in to solve for S. And I'm going to use this formula because we have radians. So we will have S, which we don't know, equals r, which we said is going to be 5.6 times 10 to the 7th, and then times theta, which is 0.00012. And then we can punch that into the calculator, and that ends up being 6,720, which would be kilometers, and that is the approximate diameter of Mars. So when you're presented with one of these problems, the distance between the two planets is going to be your r. The apparent size is going to be the theta, and then the diameter of the planet that you're trying to find is the arc length, and that's how it will always work in those problems. Now on my next page, I have an example using area of a sector. So area of a sector also has two different formulas depending on if you have degrees or radians. So area, if we have degrees, will be theta out of 360 times pi r squared. And so this is for degrees. And then if theta happens to be in radians, which it is not for this current problem that I wrote, but it's area equals 1/2 r squared theta. So that's if you have radians. Now a sector, if you visualize this, is just like a piece of pie. So if we slice out a section of the circle, theta, just like in the arc length example, it's there in the center. The radius of the circle is there, and that's all we need to know to be able to use the formula. And then here's what we'd be finding. That's the area of a sector right in there. It's just a fraction of the entire area of the circle, which is why the degree formula has pi r squared as part of its formula. And then the radian formula looks different just because once you do a conversion, things cancel in that formula. But we don't have to show that. You can just use whichever formula you feel most comfortable with. So now here's kind of a common problem. It's a cow on the end of a rope, and it's tethered, and it's going to walk in as large of a radius as it can, and we're going to solve for the total area that it can graze. So what I would do here is, if the cow keeps the rope as tight as possible, he's going to be walking around at the end of his rope, and he'll be able to swing out like all the way over to here. And then in this direction, he'll be able to swing down kind of to here. Now I know this because I wrote the problem, but I'll show you why. So 100, if he comes straight up against this wall, then the part that I already marked right here is 50. So he would have another 50 feet of his rope hanging out up here. Now, if he continues his path in this direction, and then let's say he stops exactly right here, let's draw that in. Remember, this was 50 feet of rope, so this right here is exactly 50 feet of rope. But since that one little chunk is 20, that causes this part to be 30. And then he just continues his path, walking down to here. So since that portion that I just marked 30 is 30 feet, then this part from here to here would also be 30 feet. Now let's imagine he's going in the other direction. So start back over by the cow. He has got a 100 feet of rope. He starts walking this direction. Now let's say he stops exactly in line with that 60. So right here. Well, since 60 feet has been used along the wall, he's going to have another 40 feet of rope out there, out in the field. Now, if he continues walking, he only had 40 feet of rope. So since the wall was 50 feet, let's move that 50 because that's going to look confusing. The 50 was how long this wall was, but the cow only had 40 feet of rope at this point, so this right here is 40. Let's highlight that. I'll use a different color. So the 40 goes from there to there because this was 40 also from there to there. Okay, so now the amount of field where he can graze and eat is enclosed in these. They're really quarter circles, not semicircles, but quarters of a circle. So let's just start with, let me use a different color. Okay, let's start way over here with this one. So this right here is exactly a fourth of a circle, and it has a radius of 30. And so if we use the area of a sector formula, I'm going to use this formula here because I could think of this angle right here as 90 degrees. And every single angle around this picture is all 90. So every time we calculate the area of each of these circles, it's going to be 90 out of 360 times pi and whatever the radius is. Now in that little blue portion, the radius was 30 squared. So this will be 1/4 pi, and 30 squared is 900. So let's just say, we're going to add all this up at the end anyway, so let's just say 900/4 pi. Okay, so that's for the blue. All right, now the next portion, how about if we do this part? This part right in here has another angle of 90, but now it has a radius of 50. So the next area is going to still be 90 out of 360 times pi and then times 50 squared. So that is 1/4 pi times 2500. So that's this does reduce, but I'm just going to leave it like this. That way everything will be over 4 at the end and we can add it all up pretty easily. Okay, now the next quarter of a circle is this really big one when he had his full 100 feet of rope that he could pull tight. So we have all of this right here. So again, he's at an angle of 90 right there in the center, like where his dot is. And the radius of that quarter circle is 100. So for that area, I will still have 90 out of 360 pi times 100 squared. So I'll just do the work for that. That's going to be 10,000 over 4 pi. I just simplified that all right away. Okay, so this is the yellow area. Let's go back and mark that one in between right here was the green area. And then we just have one last portion. I'll go ahead and make that pink. So this is, or purple, whatever you want to call it. So that's that last little quarter of a circle. Again, the angle is 90, but the radius of that part, I'm going to write it over here, is 40. So we're going to have 90 out of 360 pi times 40 squared. So that's going to be 1600 over 4 pi for that. So that's the purple. And then we just need to add it all up and get the total area. So I would just bust out the calculator and do it that way. So that total area ends up equaling 3,750 pi. And let's say it was in feet. I never marked it, but let's say feet squared. Alright, so just keep in mind the cow is keeping the rope tight. He's walking at the end of his rope in as far of an arc path that he can. And so you end up with 4 quarter circles. They're quarter circles because their angle is 90 each time, and so we can just follow the formula for area of a sector using 90 for the theta, and I use the degree version of that. And that's it.